Welcome to Lesson 4 of Module 2 on Recurrent Neural Networks, or RNNs. Today, we will discuss how regular neural networks compare to recurrent neural networks, or RNNs. We will then cover the RNN architecture and advantages and disadvantages. Recall that with neural networks, information goes from one layer to the next in the following order: input to hidden to output. The connections help to pass the information. Recurrent neural networks introduce a modification to the traditional feed-forward architecture. In feed-forward networks, information flows from one layer to the next in a sequential manner. However, recurrent networks allow information to travel from one unit to another within the same layer. Here is a simple recurrent unit, which is a building block of RNNs. It illustrates the flow of information within a single recurrent unit and the various components involved. The key elements are the input, the hidden state, and the output. The hidden state acts as the internal memory, capturing information from the previous time step and the current input. This information is combined through weight matrices and passed through an activation function to update the hidden state. The output is then computed from the current hidden state using another weight matrix and a bias term. RNNs can use internal or hidden states to preserve sequential information between elements in the same sequences. Hidden states are tools to model, update, and preserve the sequence information as you move from one unit, current time step, to another, the next time step. Just remember that hidden states and hidden layers are two distinct concepts in neural networks that are sometimes mistakenly used interchangeably. A hidden layer is a structural component of a neural network that sits between the input and output layers, containing neurons that perform computations. In contrast, hidden states refer to the intermediate values or activations that are passed between time steps in recurrent neural networks, RNNs, representing the network's memory of previous inputs. While both concepts involve internal network components, they serve different purposes and operate in different ways. You can build multi-layer neural networks by stacking multiple layers. You can also do this with RNNs. You simply connect the outputs from one layer to the inputs of the next layer. At the end, the output of the system comes from the output of the last layer. RNNs offer several advantages. Firstly, they can handle variable input sizes, as the recurrent units can be extended until the entire sequence is processed. This is made possible by using the same weights in each unit, similar to how the same rules might apply regardless of the specific words when learning a language representation. Additionally, the computation at each time step utilizes all prior information from previous steps, allowing the network to capture long-range dependencies and temporal patterns within the sequential data. While RNNs offer powerful capabilities for sequence modeling, they also face several challenges. One major issue is the slow training and prediction speed, as the data needs to be processed sequentially, not in parallel. Additionally, the backpropagation through time algorithm used for training RNNs can be computationally expensive. Another significant problem is the vanishing or exploding gradients, where the gradients can become extremely small or large, making it difficult to train the network effectively. Furthermore, RNNs suffer from the long-term dependency problem, where the hidden states can become corrupted for long sequences, causing the network to forget the initial parts of the sequence. You can put the components of an RNN together in different ways to build different applications. Starting with one-to-one, with one input to one output prediction. This is the same as a regular neural network. For one-to-many, multiple outputs are produced from a single input. An example is generating a text description of an image. For many-to-one, this configuration can be used for simple text classification. Multiple inputs are the words or tokens in the input sentence. The single output is the class of the sentence, for example, whether the sentence is positive or negative. For many-to-many, consider two use cases: question answering and named entity recognition. In the question answering example, a hidden state is built and then used to start producing the outputs. This is also called the encoder-decoder architecture, where the encoder part finishes processing the inputs and then produces the outputs with the decoder part. Example: language translation, where there is an input sentence, a sequence of words, in one language, and an output sentence, another sequence of words, produced in another language. The second example is for named entity recognition. In this task, you identify information or entities in text. For example, the model determines what part of speech a word is, such as a noun or verb, or identifies known entities, such as company names. Variations of RNNs propose additional mechanisms to handle the long-term dependency problem. Gated recurrent units, GRUs, introduce two gates, an update gate and a reset gate, to learn when to write to and clear the hidden states. This allows the model to better capture long-range dependencies in the input sequence. Long short-term memory, LSTM, networks extend this idea further by introducing a separate memory mechanism that acts like a memory for the whole sequence. This lesson covered a new type of neural network that is effective for sequences. By using hidden states, you can build and preserve the sequence information. Although RNNs have hidden states, they tend to have trouble with long sequences. The early information can get lost or modified. Variations of RNNs, such as GRUs and LSTM networks, try to preserve the long-term information through special gating mechanisms. These advanced architectures introduce gating and memory mechanisms to selectively retain or forget information as the sequence is processed. This allows them to better capture long-range dependencies compared to basic RNNs, overcoming the limitations of standard recurrent networks on long input sequences. In the next lesson, you will explore examples of neural networks. Thank you.